welcome. I'll tell you a little bit about this study we did over a 1 year period, examining the interaction between wet detention pond water and groundwater, kind of shifting gears here out of estuaries, going in a little bit. This does have potential implications for stormwater treatment and protection of our watershed. Quick outline of the presentation. We'll go over the purpose of the site, before we go into the methodology, and discuss the results and the implications. So summary of the project, we deployed 15 groundwater seepage meters into a wet detention pond on Florida Gulf Coast University campus. We left them there for 1 year. Did monthly sampling, and then we analyzed the flow rates and the nutrient loading through those meters. Now, the purpose of doing this actually was to determine the interactions between the groundwater and surface water in those ponds, or in this pond in particular. Additionally, we wanted to see how much nutrients were coming up from the ground into these ponds. And we also wanted to see the spatial temporal variation of that exchange. Now, this is kind of important because it is a potential source of nutrients in well-maintained ponds. This pond, in particular, is a pond not surrounded by any fertilized landscapes. It's well-maintained in a clear water state. But if it was possibly an adjacent pond that was not maintained well, we had some subsurface slope, perhaps this well-maintained pond causing problems. Additionally, these poorly maintained ponds could flow into the watershed and into estuaries into the ocean eventually. This is a number of tested wet detention ponds for the first time, as far as I know. These are often thought to be isolated systems. People will treat them as if they can dump whatever they want there and it's not going to go anywhere. So just herbicides, pesticides, maintained poorly, causing hypertrophic, but this might not necessarily be the case. So here's my excellent animation because Pixar models here. If you look at the green oval up there, that's actually a poorly maintained hypertrophic lake. I know this kind of looks like a cell biology diagram here, but that's a lake there. And then the other oval, that is a well-maintained lake or a natural lake. Then down here, this inverted lightning bolt actually goes to the river. And that's your coast there or bay. So here's what could potentially happen with some seepage and some subsurface flow. That could potentially travel to these other well-maintained systems, causing increased nutrient loading, eutrophication, and stuff like that. So our study site is located on Florida Gulf Coast University campus. It's adjacent to the solar panel fields out there. If you've never been there, it's just right next door to those. It's fairly young, it's less than 5 years old. It's a very new pond. It's about 1 acre in size. Here's a backmeasured map. You can see it's kind of steep, especially on the north and south sides. The littoral stones on the ends are a little bit more gently sloped. It is fairly rocky as well. The area here used to be quarry, some type of limestone, something like that. So it was fairly rocky, and there is limited organic sediment down there as well. Minus the really deep parts that deep is about 3 meters. Down there it does get a little bit thick in the organics, but for most of the shallow meters, they're not sitting very thick muds, very nice sand, interface between rocks. The average water column total phosphorus concentration is around 50, about 48 actually. It's mesotrophic on most of the status indexes. And as I said already, there's no surrounding lawns or anthropogenic inputs of nutrients into this lake. It's mostly surrounded by, obviously, you have these solar panels that are here to the top, and then you have some natural pine forests to the south. Alright, so our methodology for sampling, we actually employed Lee's 1977 design for groundwater seepage meters. As you can see here, here's another amazing animation of mine again. You have a 55-gallon drum, that's the big rectangle. It's kind of tilted at an angle. The reason it's tilted at an angle is you want that oxygen to the gas air feed basically putting down into the water. So you have it at an angle so that it can escape readily. And then you have a hole here at the top. You should have that hole at the highest point. That hole is connected to a hose which eventually connects to your collection bag. Now the idea of this is it seals off that sediment, and you have a set amount of water in your bag. And if there's any exchange between groundwater and surface water, you'll see that in a difference in the amount of water in your bag. So if you have groundwater coming up from the ground, your bag will expand, fill up with water. If you have water draining to the ground, you'll lose water from that collection. So it's a very easy to use seepage meter, and it works quite well actually. There consider though, it does have to be the right type of bag. You want something that's fairly thin walled that expands easily. You want to have large connections and large tubing to reduce resistance. And there's been numbers of studies on how to make it more accurate. We did follow those as closely as we could. So we replaced, we did have 15 meters, as I said. We replaced by depth class throughout the lake. We had 4 in the shallow areas. We actually had 7 between 0 and 1 meter depth, and then 4 in the other 2 classes. They were replaced randomly, but like I said, it was very rocky lake, especially in the north and south areas. So it was limited suitability of placement of 2 meters. We started in March of 2013. We're still going, but the data we have so far, February 2014. We deploy these back once a month, plus another for 24 hours. So you put them out there, you attach it to tubing. With a set amount of water, usually we use 500 millimeters. You put it out there, you attach it to your tube, you got to make sure that you don't change the amount of water in your bag. You're already doing this underwater, as you can see. It's a very tricky process, but once you get on there, you wait 24 hours, come back, collect your bag, and then you can measure volumetrically to see your rate of inflow. And when we did have an influx, we actually took that bag, sampled from it, and then froze the samples for nutrient analysis. So here's some calculations that we made for volumetric flow. That's basically just the change in volume over change in time. But you can divide by the surface area of the meter or the convex cover, which gives you a velocity. And that's actually good if you can compare between studies easily. Not every study will have the same meter, same setup. It might cover different pond areas. So it's better to have this velocity if you can compare more easily between the different systems. And then most of the time we do need a correction coefficient as well. The collective resistance of the meters does slow down the flow. What they found in a lot of meters, they put them in a tank and they'll measure the flow through the pump. To see the resistance. They can see that there is resistance from that flow. So a lot of times they add a coefficient usually is as low as 1.01, so very small, all the way up to 2, depending on the meter type and bag type. We took our coefficient as 1.25. We borrowed that from the literature, using meters that are very similar to ours as far as setup, bag type, connection quality, stuff like that. And then for nutrient analysis, we measured TN and TP. For TN, we used a newer method using second derivative spectroscopy. And then for TP, we actually used the standard procedure for surface and wastewater. So the results, here's the mean flux velocity by month. You see, we started in March and ended in February. The results are very small. They're in centimeters per hour. That's the most commonly reported way of reporting seepage flux. But these could easily be represented in millimeters per day, something like that. Bigger, but these are pretty normal numbers for a natural lake. So you can see there is a lot of variability throughout the year. There's not much of a trend to be seen, really. You can see that June is kind of the lowest point here, with January being highest. But again, the data doesn't really support any real trend. I do have a theory about June. Somebody asked me again, maybe I'll share that with you. But no real statistical data to support it. So here's comparisons of the flux velocity by season. Over to the left, that is the dry season, which seems counterintuitive. You actually have more flow, statistically significantly more flow, in the dry season when compared to the wet. And here's absolute flux velocity by depth class. The reason I use absolute is some of these meters would show inflow and outflow, so if you average them, we could do a zero for flow. So I'm going to use absolute to see the total amount of water being exchanged. This graph here shows that the shallow meters, 0 to 1 meter deep, has significantly more flow compared to meters in deep parts of the lake. So it's showing you that the shallow regions exchange more water from groundwater than the deep regions. This has been shown in much literature before. And here's more of this is the spatial variation in the T and the TP fluxes. So we did take these measurements from the bags and sample and analyze these for nutrients. And this is the flux rates that we found. You can see here that the shallow meters kind of show the highest amount. That does kind of have to do with them having more influx in general. But spatially, it is very highly variable. We also have a lot of error, especially in some of these shallow meters like A7. Huge error bar chart through there. But it just goes to show you how variable it is as far as TNT graph will show this in just a second. Again, the trend does tend to follow the flux trend, the raw water flux. It does follow the TN and the TP, especially the TN. The TP is a little bit different. It's a little hard to tell. This graph does show a little better for their setup, and you can see the TN. You can see high variability, high error bars there, especially in November and December, which were kind of anomalous in their flux rates. And phosphorus is a little tighter, except for February, where we had some high levels as well. Okay, so this is our extrapolated flow map. We created this using the server. You can see this kind of gives you a better idea spatially what we found in the pond. More red, that's more inflow, and that's the extent of that purple or blue color, that's outflow from the pond to the ground. So as you can see in the north side, especially the northeast corner, kind of had a lot of inflow, while the southwest corner and south side had a lot of outflow. And that kind of goes along with the general idea of how groundwater flows in southwest Florida, which is kind of in a southwesterly direction. So you can see it kind of comes in that side and eventually makes its way out the other side. So the flux rates that we found were very similar to natural lakes. They do seem small just because of how the units are set up in the numbers, but they are very similar to natural lakes. As I said, there's significantly more flux overall in the dry season. Again, it's counterintuitive. It seems like there may be some delay to the inflow into these lakes. There was significantly more flux in shallow meters as well. It's very significant. But again, this is told in these studies previously to this. And as you saw, there's limited temporal trends in the nutrient flux. Now this is an interesting graph here. This is comparing flux velocity, centimeters per hour down at the bottom, and then TP concentration, measured concentration on the y-axis. These are log scales here, but you can see there's a downward trend. As flux velocity is increasing, the total phosphorus concentration is decreasing. And there is some precedence to this. As the water is flowing up from the ground, if it stays in these meters a long time, there a lot of gallons to be filled into these meters before it makes it out the top of that hole. So if the water's in there for a longer period of time, it's likely that that's causing an increase in total phosphorus values, likely because of the chaos conditions in there reducing, causing the release of phosphorus from bound iron. Ballinger in 1985 says this already. There could be possible overestimates, especially in phosphorus, using conventional seepage meters. Now, we have a potential fix for this, and we would like to employ is using 4 water wells adjacent to seepage meters. So you, instead of taking your sample for nutrient analysis from your bag, collection bag, you actually take it from a 4 water well, which is adjacent to your meter. And that should get rid of this problem here, and then you take your volumetric flow straight from your meter. The overall water and nutrient contribution via groundwater has not yet been determined. We hope to do that soon with meteorological and hydrological data. In the area, there are several groundwater wells located on campus. We do hope to do another year study on this as well. That could help identify some of the trends that were kind of missing or noisy there. And hopefully maybe see, add some hydrological data to see any precipitation or the hydrographs of groundwater to show in the trends as well. So in conclusion, the soil field pond did show inflow of groundwater and outflow, and at the highest indicator of 17 milligrams per liter of total nitrogen, and 1.14 milligrams per total phosphorus. Now, this is the precedent for pond maintenance, as I said. If this pond is showing significant inflow and significant outflow, this pond is not really an isolated system. For example, there are close to 30,000 detention ponds in the southwest Florida area. If some percent of these ponds are poorly maintained, highly eutrophic, high amount of organic sediment, and then have high outflow exchanges into the groundwater, this could potentially be a problem to the watershed, problem for other people who are trying to maintain the ponds in the correct or good fashion. So it just goes to show you that responsible pond management is important, and it's not as easy necessarily to consider these isolated systems and just kind of dump anything you want to without consequence.
time for questions.
Hey Mark, Mike Berger with Stantec. So what would you say your implications are in terms of maintenance? Do you have some recommendations in terms of maintenance that are different than the current practices? And also, do you see alternatives to wet detention as a better way to capture and treat stormwater runoff?
So right now, a lot of people, especially detention ponds found in housing communities, they'll maintain the pond like a golf course pond. So they want no vegetation around it. They want lawn growing right up to the edge, and then fertilize the heck out of it. So that's something that really stops as you're dumping these fertilizers into the pond. And then you're also these people that like to remove their macrophytes that spray the algae. This is just causing a really fast load of organic sediment building up down there, which is just causing a lot of problems to maintain that pond, causing it to be hypertrophic. And then also those herbicides and pesticides you're using on the lawns, as well as algicides in the water, kind of as a band-aid for this. So they get this large amount of organic mud, they spray these weeds, it all builds up, and they just keep spraying. It just gets worse and worse. So it's a really bad way to manage the pond, rather than naturally where you encourage macrophyte growth around the edge. You don't fertilize the lawn so intensely right around the lake as well. So those pond management practices, the natural ones, are better. Also, the use of aerators to prevent fragmentation on the bottom of the pond. That's a good way as well to kind of facilitate improvement of the pond. But again, if you're dumping copper sulfate consistently into the pond, that's not a great way to do it. Alternatives to the detention ponds. I think it's really one of the best ways to go. They are both practical, easy to implement, and they are good for recreation and for housing. A lot of people like to have their house on a detention pond. It doesn't increase property values. So I think it's a good way to do it because it does slow down the flow into the watershed, especially for stormwater. But I just think proper maintenance of these ponds because it's more important.
Mark, from your experience, do you have any way hints for working with homeowners to encourage them to use these practices?
I haven't worked with homeowners directly. Dr. Thomas, who you'll hear from in just a minute, I believe, he does work with homeowners quite a bit. If I had to guess, or if I had any to all, it would be about education. The more they're educated about systems and how they operate, they're going to make more informed decisions on how to maintain the ponds.
Mark, hi. I'm not so sure if this is so much a question or a comment. Do you work with the water management districts, for instance, in agricultural areas, a pond that is 15 acres in size or less is completely and totally unregulated in terms of steeps of slopes, any kind of political plantings, hypoxia, everything's unmeasured, it is completely and utterly exempt. Do you think that your study has implications for agricultural areas as well, given herbicides, pesticides, cows? Kind of a loaded question, but is there a connection to the water management?
It remains to be seen. You have to study on these ponds to see how they're interacting. Every pond will be different, but if this is applicable to these types of ponds, they're found in farmland. Yes, this is significant. If these are especially agricultural areas, that's where you're getting the highest amount of anthropogenic nutrients coming into and plant. Really, we fix so much nitrogen nowadays to dump on our plants. If that's all made into this pond, let's say your 15-acre pond, for example, and then go into groundwater, that can be a problem, especially with herbicides and pesticides as well.
Thank you.
Thank you, Mark.
Future presenters, this is the right size scale to use on your presentations. That was very readable, very well done.